Welcome to one more video on KBC. In this we will see potential divider and its applications, so which is very commonly used in many electronic circuits. Okay, these are the prerequisites you should know. Very simple Ohm's law, KVL, KCL, and of course you should know the BJT operation. Okay, these usual thing we'll start with. Okay, this is the circuit what we are considering. So usually in electronics, it so happens that we will be using a DC supply of 5 volts usually for many of the experiments. Sometimes maybe in simulations we may use a DC voltage of 1.8 volt, 2.5 volts, or maybe in some experiments we will use a 12 volt power supply or 15 volt power supply, all those things. So this is the range of power supplies that will be used in many of the circuits. Assume that you want to get a voltage of maybe 1.23 volt, and assume that you want to get a voltage of maybe 0.83 volt, and if you want to get a 0.21 volt for a certain application. So in such case, these are all the standard voltages you can think of, and there may be some battery of 9 volt available, so which will be a battery of 9 volt. And suppose if a particular application requires a non-standard voltage, then how do we get it? The solution is potential divider. So you have the standard value of this whatever 5 volt, 12 volt, 15 volt you have. Assume that I have a 5 volt battery, and 5 volt battery in the sense you may have a regulated power supply using 7805. You're getting a 5 volt output voltage with with a certain maximum DC voltage. So you're getting a 5 volt supply. So that's what is here. So from this 5 volt you want to get, assume that you have to get 1.83 volts for a certain application. So now in such case, how do I get exactly 1.83 from the available 5 volt? So we will use potential divider. So before we proceed on to potential divider, let us also talk about what is the series resistance of a usual voltage source. So we say that okay, this is the voltage source. So this is how it is represented. Typically in most of the cases, we consider the source resistance of these sources as almost equal to zero. But practically we're going to have few ohms of resistance, but you can certainly neglect, and we typically consider it as 0 ohms. So meaning that whatever 5 volt that is available from this battery is available for usage also. This is, if you are using a battery connecting to this, you'll be getting 5 volt. So that's what is a battery of 5 volt. So source resistance of this battery, whatever 7805, is having zero source resistance. Assume. Okay, this is assumption as well as true also. Now I have to get 1.83 volt. Now the question is, I have to get 1.83 volt. So now we have to see whether this 1.83 volt I'm getting, will it be of having some source resistance or not, because we don't have a regulator of 1.83 volt, or we don't have a regulator of 0.21 volt, we don't have a regulator of 2.62 volt. So these are all derived from the available power supply. So what we'll do, so this is my 5 volt power supply. I will use two resistors and try to get the Vx or the desired voltage, which may be 1.83 in this particular case. Then how do we decide the value of R1, R2? So we can certainly decide the value of R1, R2 because you're looking at 1.83 volts. So let me assume the value of this as 10 kilo ohm. So I need to find the value of this R2 so that this voltage is 1.83. Now we know that from this equation we can write a KV, or we can write a what expression for Vx. So what is expression for Ix? By considering a loop current of I. So now Vx is given by the current flowing through R2 and the resistance R2. But what is current flowing in the circuit? It is V1 by R1 plus R2. R1 plus R2 is the current multiplied by R2 is the resistance. So this comes out to be V1 into R2 by R1 plus R2. So this is what is the voltage that is still going to have. So now since we know that this has to be 1.83 volt, because I'm supposed to find the value of R2 now. This is 1.83 volt is equal to V1 is 5 volt. So R2 I need to find. So this is 10 kilo ohm and this is again R2. So let me solve for R2. So when I'm solving for R2, so it comes out to be, so it is 1.83 alpha equals, open the parenthesis, 5 into alpha A, close the parenthesis, divide by, open the parenthesis, 10 exponential 3 plus alpha A, close it, shift cal. So I'm getting the value of R2 as 5.77 kilo ohm. So this is the resistance of this. So this should be 5.77 kilo ohm. Then I should get a resistance of, sorry, a voltage of 1.83 volt at this point. Now, is this source? So whatever now you're getting the resultant of this is something like this. So this is now 1.83 volt. So this is this. So does this source, does this potential divider, will it have some source resistance? Now that's the question. So what is the source resistance of this? Source resistance of this source is not zero, whereas the source resistance of this source, which is the power supply, was zero. But here this is not zero because you are using R1 R2 to derive 1.83 volt. So what is the source resistance? The source resistance of this is the R Thevenin, because this is nothing but the Thevenin voltage Vx, and whatever resistance I'm going to see from here is nothing but R Thevenin. To find R Thevenin, we know that we're going to short this source, and then whenever I short, this R1 R2 will come in parallel. The effective resistance are the R Thevenin. The resistance looking into this node is R Thevenin. So that is given by parallel combination of R1 and R2, which is nothing but 10 exponential of 3 inverse plus 5.77 exponential of 3 inverse equals and whole inverse. So it is now 3.65 kilo ohm. 3.65 kilo ohm. So let me tell you how did I find this R Thevenin. So this is, so R Thevenin is nothing but, you're going to have an equivalent circuit something like this. This is R2, this is R1. You are seeing across this, so it is now R1 parallel R2 is R Thevenin. So R Thevenin is nothing but R1 R2 by R1 plus R2, or this is also equal to R1 1 over R1 plus 1 over R2 whole node, correct? So this is the value of R Thevenin. So this can be rewritten as, so in calculator you can simply write it as R1 inverse plus R2 inverse and its whole inverse. So that's what I did here. So this is actually 10k inverse plus 5.77k inverse and whole inverse, which is coming out to be 3.65 kilo. This is what R Thevenin. Now this source, whatever we considered, this potential divider source, what I have considered, will be now looking like 1.83 volt, and this is 3.65 kilo ohm. So now this is 1.83. So this is what is the equivalent circuit of this. This is now represented by this. So from a 5 volt power supply having zero source resistance, you can get a potential of 1.83 with some associated source resistance. Source resistance cannot be zero for this because you're actually obtaining a secondary voltage from this. So this is derived out of 5 volt. This is derived out of 5 volts. So this is what is R Thevenin. So this is typically V Thevenin, the Thevenin voltage. Okay, fine. So now let us uh, try to see in LTSPICE if you want to change this voltage, to change the voltage of this. Okay, let me just have a look at this. Assume that this is some 5 kilo ohm, and I want to know what is the value of Vx. Assume that this is again 5 volt. I want to find the value of Vx for, so let us say this is R2 for different values of R2. So when R2 is equal to 1k, what is the value? When it is 5k, what is the value? When it is 10k, what is the value? So I want to know the values of Vx at three different values of R2. So how do I do that? So of course we know that in practice or in labs we're going to have a DRB, a switch will be there where you can able to vary the resistance. But in simulation, how can I do this? How can I do this? So let us try to do it. And okay, what is, so maybe before we go to simulation, let us find out what is Vx expected for R2 of 1k, 5k and 10k. So now what is Vx? Vx is given by V1. If I name it as V1, R2 by R1 plus R2. Now this is R2, and let me say this is Vx. So this is 1k, this is 5k, this is 10k. I can straight away write for 5k I'm going to get 2.5 volt, because this is 5k, this is 5k. When the equal resistance are there, this voltage will be equally divided between these two. So that's why 5 by 2 is 2.5. When it is 1k, so what I'll do, it is 5 into alpha a, okay, close the parenthesis, divided by, okay, this is now I made it 5 exponential of 3 plus alpha a, close, calculate for 1k. So it comes out to be 0.833 volt. Calculate for 10k, it comes out to be 3.33 volt. So these are the voltages that we are supposed to get for a Vx of, sorry, for a R2 of 1k, 5k and 10k. So let us go to this LTSPICE simulator. So I already have the circuit here. Now let us do one analysis. Let me run this .op, because now we are trying to see only the voltage. Now since it is 1k, you can see the voltage, that is V of Vx is 2.5. So that's what we expected. Suppose if you make it, what 10k, we are supposed to get it as 3.33 volts. Just have a look at this. Was it 10k? Just a minute. Where we actually did the mistake. Okay, this should be 5k. This is actually, because in my simulation we took it as this is 5k. Okay, 5k. Okay, with this 5k and 10k, if I run, I have to get 3.33 volts. Can you see here? You're getting 3.33. So if I make this equal to 1k, if I make it equal to 1k, I have to get 0.83. This is 1k. Can see this is 0.833. If I make it 5k, it will be 2.5. So that's not the intention. The intention is not change this value one by one, but I have to change this value in a single simulation. The value of R2 changes from 1k to 5k, 5k to 10k. That can be done in simulation. For that, go to this SPICE directive. When I go to this SPICE directive, this editing window will come. Here you right click. When you say right click, help me edit, just over here select step command. Can you see there is a step command where you can able to change some parameter stepwise? You can change this parameter by stepwise. So before I do this, so whenever whichever component or the value you have to change, you have to replace this value by something within flower bracket. So I'm just putting something in flower bracket. Let me say it as RVAR. So now, since this value of R2 is not a fixed value, you're changing that. Let that value of that parameter be RVAR, stands for R variable. You can just give you a name. So now let us go to this here. Let me help to edit. Let me go to the step command. In this step command, which parameter you want to change? You want to change RVAR. So let me change, let me list the values that you want to change. So let me change this to 1k. Sorry, let me go back here. This is 1k. Next it is 5k. Next it is 10k. So these are the three values of RVAR values that you will be considering. See here, this is a dot step command where a parameter is changed by name RVAR with a list of values as 1k, 5k, 10k. So if I do the simulation, you can see now these are the values. Now you can actually uh, plot what it is here. Can you see here? Can you see it is giving the value at this point? Because this is the value on x-axis. What you have on x-axis, you have the value of R2 as 1k, 5k and 10k. Maybe you can just click on this and go over here. So this is the first value. Can you see it is 833 millivolt? And of course in between this is not valid because it has simply plotted the graph. So it has joined the three lines. So this is for 5k. For 5k it's here. For 5k you can see it is 2.5 volt. For 10k, it is 3.33. So this is one way. There it is listing in terms of the value of R2. So what you can do is you can do a time response also. So what I'll do is I'll go back to this. Okay, let me just do dot run. The moment I do dot run, it will ask for some time. Let me give it as some 10 milliseconds. Now run, when I run, can you see here? This is the first value is, this is actually listing different values of Vx. Can you see the first value is 833 millivolt. For the second value, just okay, press your arrow key. See now the second value is 2.5 volt. The third value again go up. It is 3.33 volt. So these are the values of course these are the this is with respect to time. This is the value of Vx when R2 is 1k. This is when it is 5k. This is when it is 10k. So we can able to run either .op or .tran with variable values of R2. The parameter, okay, how do we do is, so let us click on this. That is, you click on this, of course this should be highlighted. Then you have to go to this uh, spice directive. In this spice directive you may have to right click over here and then you have to go for this help me edit. So here you have to select dot step. In this dot step you have to start with the name of the parameter that you're changing, that is RVAR, what type of variation, whether you're varying the value or whether you're having specific values. So let me see how do I use that variable value. So I want to vary this value of let me come back here. Assume that I want to vary this value of R2 from 1k to 10k in steps of 1k. So I want to know what is Vx at 1k. 2K, 3K, 4K, 5K till 10K. So how can I do that? So that can also be done. So there, this dot step should be different. Dot step should be linear. You have to start from 1K, go up to 10K in steps of 1K. So now it's a dot step param. There is no list now, so the list is missing. List is for specific values. This is over a range. It's a linear sweep. It changes. R2 changes from 1K to 10K in steps of 1K. If you run it now, you'll have different values. Can you see? This is, you have 10 different values. So this is for 1K, 2K, 3K, 4K, 5K. So of course, how can you do that? So you can come here, escape, just press once here, you get the cursor. This is, you can see, this is there at the bottom most. Can you see this dotted line? Press the arrow key. It is the, for R2 is equal to 2K, R2 is equal to 3K, R2 is equal to 4K, R2 is equal to 5K. You can see we have got it as 2.5 earlier also. Then it's 6K, 7K, 8K, 9K, 10K. But 10K it is 3.3 as we saw earlier. This is how we can uh, use a potential divider for dividing the voltage. Let us see the application of this potential divider. So usually this potential divider, simply we cannot will not be using it for just reading the voltage. The most commonly used application of potential divider is in biasing of MOSFETs, biasing of BJT circuit. I think you might have studied that in your classes. So we have a potential divider biasing. Potential divider biasing. This is the potential divider biasing. Okay, for that, so let us consider the circuit here. This is the circuit what we are looking for. This is how we do it. This is VCC and this is a BJT. Let us say this as R1, R2, this is RC. This is effectively a potential divider. Now I want to bias this transistor, because usually we know that biasing will be done with some a Q point in mind. The Q point is usually, we will take it as, okay, this will be around maybe 1.1 milliamperes. Let us take it as 1.1 milliampere, and let us take it as 2.5 volt. What is 2.5 volt? We know that Q point is IC and okay, let me take it as 1 milliampere, IC and VC. IC and VC. So what is the current flowing through this collector terminal, and what is the voltage between this collector and emitter? So I want to design a Q point of IC is equal to 1 milliampere and VCE of 2.5 volt. Now, whenever we actually design, we have to have the specifications of a MOSFET. So I have actually found the specification of the MOSFET by doing some simple experiment. So it was found that for this BJT, we need to know two parameters. One is reverse saturation current and other is beta. Beta is found out to be 200 for a transistor which is SL100 that I'll be using now in my actual circuit, and the IS is reverse saturation current is found out to be 59.5 into 10 power minus 15 amperes. So this is the reverse saturation current, and this is, so you can almost take it as this is 59.5. Okay, with these specifications, let us start with the design. So because I need to use this, I need to design the values of R1, R2 so that I can achieve this particular specification. So now to start with, so let us do the exact design. So one of the equation what you have is IC is equal to IS exponential VB by VT. So from this we are deriving the expression VB is equal to VT ln of IC by IS. So now I can find the value of required VB because I know VT, I know IC, I know what is IS. So it is 26 millivolt ln of IC is 1 milliampere divided by 59.5 into 10 power minus 15 is the value. So let me find out that it is 26. Okay, it is 26 exponential of minus 3 into ln of 1 exponential of minus 3 divided by 59.5 exponential of minus 15. So now the value comes out to be, so this is 0.612 volt, 612 volt or 612 millivolt. So this is VB required. So I know what is the VB required. So now once you know VB required, this is what is VB required from here to here. This is VB. Now can I write the equivalent circuit of this? So this we know that. So in the previous itself we know that we can replace this entire potential divider by a power supply and a RThevenin. Now can I replace this VCC R1 R2? Okay, let us assume that this is 5. Shall I replace it by something like this? This is V Thevenin and this is R Thevenin and this is what I am having. This is 5 volt. This is RC. Correct? So now I need to, so this I need to design. So I need to design what is VTH and what is this value. Now I shall proceed now. This is let me consider the 14th one. Okay, now can we write an expression as VTH is equal to do we have this as IB into R Thevenin plus VB? Can I write it? I can write this. So this I can write. Now what is VB? We know the value of VB as 612 millivolt. How about IB value? Do I know the value of IB? Because I have this equation, I need to solve for VTH and RTH. So what is this? So this is IB. IB is given by IC by beta. So it is 1 milliampere divided by 200. So it is 1 exponential of minus 3 divided by 200. It happens to be 5 microampere. 5 microampere. So I know this, but I don't know two parameters. So now what I'll do is, what is VThevenin? VThevenin is equal to, so what is this VThevenin? So VThevenin is VCC R2 by R1 plus R2. What is RThevenin? RThevenin is R1 R2 by R1 plus R2. Correct? So now uh, can I write this as what is uh, R Thevenin by R1? Can I write it as R2 by R1 plus R2? Correct? I can write it as this. And let us assume uh, the input resistance of this MOSFET, let it be around 25 kilo ohms. So what is this input impedance of a MOSFET is? Because whenever I want to design a circuit, this is where I'll be applying the input voltage. So let the input impedance of this be high. So we will try to see why it should be high, all those things later. Let this be 25 kilo ohm. If this is 25 kilo ohm, then this R in is also equal to R1 parallel R2, which is nothing but R Thevenin. R Thevenin. So now what I'll do, I will substitute the values of, so now I will replace this equation by, what is that equation now? So V Thevenin, so now this, what shall I replace this by? I will replace this by, so I will replace this by, so it is V Thevenin equals VCC. So R2 by R1 plus R2 is nothing but R Thevenin by R1, correct? And shall I write this as VCC into R Thevenin by R1 is equal to IB is 5 microampere and R Thevenin is 25 kilo ohm, and what is this VB? VB is 0.612. So now I will solve. Of course this R Thevenin is again 25k, and what is this VC? This is 5. So I will now solve for R1. So what is R1 now? So it is 5 into 25. Okay, let me just do this. 5 into 25 exponential of 3 divided by alpha. Okay, let me just put a parenthesis. 5 into 25 exponential of 3 divided by, okay, let me close the parenthesis, divide by alpha a. Okay, I would have put one more parenthesis here. This is 5 into 25 exponential of 3 close divide, sorry, this is 5 into 25 exponential of 3 close divide by alpha a close alpha equals, it is 5 exponential of minus 6 into 25 exponential of 3 plus 0.612. Shift cal, it will give me the value of R2. Sorry, R1. So R1 is coming out to be 169.2 kilo. This is the value of R2. The value of R2 is 169.2 kilo ohm. So then what is the value of R2 now? So now we know that uh, R Thevenin is equal to R1 R2 by R1 plus R2. R is equal to R1 inverse plus R2 inverse whole inverse. So I can say this as 25 exponential of 3 alpha equals, open the parenthesis, it is 169.2 exponential of 3 inverse plus alpha a inverse close whole inverse shift cal. I'll get you R2. So R2 is coming out to be 29.33 kilo ohm is the value of R2. So how much is R1? R1 is 169.2 kilo ohm. So this value of R1, R2 and VCC of 5 volt will give me 0.612 with a input impedance of 25 kilo ohm, with an input impedance of 25 kilo ohm. And if you are having 1 milliampere flowing, if you connect 2.5 kilo ohm resistor, so there's a drop of 2.5 volt will happen and you'll get the required VC. So let me just go to this simulation. Where is the simulation? It's here. I will open. Okay, let me close this and let me open this. So this is, let it be 2.5k and let us make this as 169.2k, and this should be how much? This should be 29.33k. See, IS is 59 e power minus 15 and this is beta factor is 200. This should give me a collector current of 1 milliampere, close to that. So let me run this. Let me save it first. Let me do a dot op now. Let me see. Yeah, I'm doing a dot op. Run this. Let me just go here and then try to see what is the net log. See here. Do you see a collector current of almost 1 milliampere? Can you see a VC of almost 2.43 volts, which is the expected value? Meaning, this is the exact design. If you are using a 2.5 kilo ohm, of course, let me just change that number, otherwise you'll get confused. So this is R1, actually R2, this is actually RC. This is RC. So I have slightly let us see the simulation, sorry, the working of this in the hardware also. In the hardware, let me use it as 2.2k. I'll use it as 2.2 kilo ohm because I'm using a standard resistance. So here I'm using two DRBs to set the value as 169.2k and 29.3k. And if I run this, I should get these values. You can see the current is almost same. It's 1 milliampere. Okay, let me show you here. Let me show you this. See here, can you see the current is almost 1 milliampere? The VC is 2.73. So let me write for a value of 169k as R1, R2 as 29k, and this as 2.2k. The VCE is getting as 2.73 volt and current is almost 1 milliampere. Correct? This is what I'm looking at. Is 169.29. So let me go to the circuit here. So let me switch this. I'll show you the real circuit what is connected here. Let me change this. Okay, can you see now? I have a power supply of 5 volt. I have a transistor whose can you see this is the S-cylinder transistor, and I have two DRBs. This is for R1, this is for R2, and I used a fixed resistor of, you can see I'm using a fixed resistor of, this is 2.2 kilo ohm resistor. And let us see the, okay, let me set the value of resistance to 169k. Let me, for the time, let us switch off this. It is 169k and this should be 29k. This is 1020. This is 89. This is 129. So this is 29. Okay, 29.3 is there. and this is 169. Let me turn on this. See now, this is the value that I've set. So this is the value of that I've set. The value that I've set is 169K and 29.3K, and this resistance is 2.2K. We are expecting a current of 1 milliampere. This is the practical circuit. So you can see I'm having a practical circuit that is being connected. You can see now you are having a current of almost 1 milliampere. It is, can you see, it is 0.93. Maybe if you want to get exactly 1 milliampere, you may have to slightly change this value. You can see I'll just slightly increase the value of R2 by hundreds of ohm. Can you see it's increasing? Can you see now it is very close to 1 milliampere? This is how you can adjust. Now what I'm doing, I'm increasing the value of R2. I'm increasing the value of R2 so that it is coming close to, can you see now it's almost 1 milliampere? It's exactly 1 milliampere. Can you see the corresponding uh, collector voltage? Can you see it is 2.73? Can you see it is 2.73? So meaning, if I'm now, why I've slightly adjust this, because this is the practical circuit, the values may slightly change from then to now and now to later value. So you may have to this is not changed from 29K to a very large value. 29.35 I have just changed it. So this is a very small change in terms of hundreds of ohms that I did, so that now I'm making a current of exactly 1 milliampere and a drop of the collector voltage is at 2.73. This is exactly what we got in simulation also. Let me show you the simulation. Maybe I'll show you side by side both the simulation value and where is my simulation value? It's here. You can see this outlog. You can see my values over here. You can see this is 1 milliampere 2.73. Can you see here the current is 1 milliampere, it is 2.73. Can you see the same thing here? This is 1 milliampere and this is 2.73. This is the real hardware. This is from the simulation. This is from the design. So all the values are okay. So we were supposed to get a VP of 0.612. You can just verify. So I'll show you that VB also. VB comes out somewhere here. See that? Is it not almost 0.612? It is so perfect. So now why we could able to get all the values same is because we have assumed the value of beta as 200, which is there for the case this is already measured, and the value of IS is 59.5 into 10 power minus 15. These are the measured values of this MOSFET, sorry, this transistor, and the same value is used here also. Can you see here? The same value is used here. So whenever the same values will be used in simulation, design, and in practice, there is no variation in the values of the practical value and the design value and the simulation values. In the simulation values, all of them will perfectly match to each other. This is the exact design of potential divider, which is very easy. So what is that we assumed? Let me just go back here. Let me make a recap. The recap of this usage of potential dividers, we just used it for, okay, let me just make a recap. We started with using this potential uh, divider for my biasing circuit, which is R1, R2, this is RC, you have a VCC, and this. You started with a model parameter of beta is equal to 200 and IS was 59.5 into 10 power minus 15 ampere. Then we assumed, okay, during the design, of course, we have two important equations of VBE and this equation, or the expression for IC is equal to beta times IB. Using these two equations, we got the value of what should be your VBE, then this is what is VB required. So then you replace this R1 R2 and VCC by V Thevenin and R Thevenin. Here we made one assumption that, so what is the major assumption we did is, so we assume the value of R in, which is nothing but R Thevenin, to be 25K. So this is a typical proper assumption of a larger input impedance. So it cannot be like, okay, 200 ohm, it cannot be like 2.5K, it cannot be like 10K. So let it be 25K, even if it is 50K, it is good. So you have to have larger input impedance. With this assumption of 25K, we got the value of R1. So once you know R1, once you know R Thevenin, you can easily find R2. Once you are done with R1, R2 values found out, you can connect those component values using uh, the DRB, whatever you have. Assume that if you don't have a DRB, then you have to go for the nearest possible value of R1. So see in the lab what is the nearest possible value. Suppose if you don't have a nearest possible value of this as 169, assume that you don't have DRBs, then you can choose this as 220 kilo ohm. You can choose it as 220 kilo ohm. The moment you choose it as 220 kilo ohm, this will change. So let me just redesign this for the available standard resistance. If this is 220, then what does this R2 becomes? So now uh, okay, let me just go to this 220. When this is 220, so I'm just going to the nearest possible value of okay, the moment you make this 220K, so let us see what happens to that. So if it is 220K, what will be your of course when this is, you have this expression. Whenever this R1 is 220K, you can actually re-estimate the value of IB and all those things, and then of course maybe you can see once you are done with this, you can connect a 220 kilo ohm. I'm just making this, so this is 220 kilo ohm. The moment I increase that resistance to 220 kilo ohm, you can see here, when I'm going for a standard value, so this is increased to 220 kilo ohm, and you can see this current has reduced. Now you can increase this value of R2 so that this current increases. Now I'll make it 3 point, okay, maybe this is 39K. You can see now I will use 47K resistor. You can see this is 220K, R1 is 220K, this is 47 kilo ohm, which is a standard value, and you are having a current of 1.18 milliampere, and that will result in a VCE of 2.3 volt, which is fairly good. See now, we are now using R1 is equal to 220 kilo ohm, which is a standard resistance. I am using R2, which is a 47 kilo ohm. This is also standard. Now these two are standard values, and I'm still getting with a value of RC is equal to 2.2 kilo ohm. You can see I'm getting a current of 1.19 milliampere. More than that, can you see this is almost 2.32, which is okay for your design. So now if you actually find the input impedance is more than 25K, which is always good. So now you can make it, so you can find what is R in here. R in is a parallel combination of this, which is 220 inverse plus 47 inverse, whole inverse is 38K. This is 38K. So 38K is very good compared to 25K. So even without using DRBs, you can, of course, I can replace this and put a 220 kilo ohm, this as a 47 kilo ohm, I'll get the same current, I'll get the same design. So this way, no need to always hang on to the DRB values. Once you get a range of values, then you can slightly vary the resistances for the nearest possible standard value, you can still get the design what is desired for, what is desired for. Okay, then thank you so much. Maybe if I just go back to my simulator and then redo the same thing, we'll get the same thing. I'll make it a standard value of 220k. This you cannot start in the beginning itself because you'll not be knowing the range. So, and this will not be true for all the transistors. Suppose if you change the transistor, that will totally change. This is 47k. Suppose if I run it now, and try to see the voltages. So what I'll do is I'll go to this view and then output log. Can you see the current is 1.36 and can you see this is almost 2 volt? That's what we got almost there. So this is how the values you can able to change. Fine. So thank you. Of course, these values in simulation you can get whatever value, but when it comes to real usage in your lab, you have to be careful. So this is the value what I'm getting. Thank you.